Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on electrostatics and magnetism. Let's go ahead and get started. This says for questions 1 through 3, refer to the figure below, in which F represents the electrostatic force exerted on charged particle S by charged particle R. Question 1 says, in the figure, the magnitude of the electric force on R due to S is blank. Now, in this question, we're asked to determine the magnitude of the electric force on R due to S. In the figure, it shows these two charged particles, R and S, exerting an electrostatic force on each other. Now, this force is represented by F as we see it in the diagram. And according to Coulomb's law, the electrostatic force between two charged particles is given as K, Q1, Q2 over R squared, where K is Coulomb's constant, Q1 and Q2 are the magnitudes of the charges on particles R and S, and R is the distance between the two particles. Now, in this problem, the figure already indicates the magnitude of the force between R and S. It's F. So according to Newton's third law of motion, the forces between two interacting objects are equal in magnitude, but opposite in direction. That means that if F exerts a force of F on R, then R must also exert a force of F on S. Hence, the magnitude of the electric force on R due to S is simply F. And the correct answer for problem 1 is B. Problem 2 says, if the distance between the centers of the spheres is halved, the magnitude of the force on S due to R will be blank. So here we're going to take advantage of Coulomb's law, which says that the force is equal to K, Q1, Q2 over R squared. Now, what we see is that the force is inversely proportional to the square of the distance between the charges. That means that if the distance between the charges decreases, the force will increase. And if the distance increases, then the force will decrease. Now, in this case, we're told the distance between R and S is cut in half. If the original distance was R, then the new distance becomes R over 2. So let's go ahead and take R over 2 and substitute it back into our equation. What we get now is that the electrostatic force is equal to K, Q1, Q2 divided by R divided by 2, and that's all squared. Now, if we expand on this, this is going to look like K, Q1, Q2 divided by R squared over 4. Now, in the denominator, we have R squared divided by 4. This is alternatively written as 4 multiplied by K, Q1, Q2 divided by R squared. We notice this part of the expression is just Coulomb's law, and it's multiplied by a factor of 4. So that means that when the distance between the spheres is cut in half, the force becomes 4 times greater than the original force. Therefore, the new magnitude of the force on S due to R will just be 4F. And that's going to be answer choice D. Let's move on to problem 3. Problem 3 says, assume the direction of F is the same direction as the electric field between R and S. If an electron were placed midway between R and S, the resultant electric force on the electron would be blank, towards R, towards S, upward in the plane of the page, or downward in the plane of the page. Okay, so let's talk about this. The electric field is a vector field that represents the force per unit charge that a positive test charge would experience in the field. The direction of the electric field at a point is going to be the direction that a positive charge would be pushed or pulled. On the other hand, an electron, which has a negative charge, will feel a force in the opposite direction of the electric field because of its negative nature. So keeping that in mind, let's take a look at our diagram here. The figure shows an electrostatic force F directed from S to R. This suggests that S is a positively charged particle and R is negatively charged because electrostatic forces are attractive between oppositely charged objects. Therefore, the electric field between R and S will point from S to R, from positive to negative, as the electric field always points away from the positive charges and towards the negative charges. Now, an electron that's placed midway between R and S, what's going to happen? The electron has a negative charge, so it's going to feel a force in the opposite direction of the electric field. Since we just said the electric field is pointing from S to R, the force on the electron will point from R to S. That's the field that the electron will feel. And so the correct answer for problem 3 is going to be B. The electron is going to be directed, the force on the electron will be directed towards S as the electron moves opposite to the electric field direction. Wonderful. Let's tackle problem 4 next. Problem 4 says, if the electric field at a distance r away from a charge q is 36 newtons per coulomb, what is the ratio of the electric field at r, 2r, and 3r? Okay, the electric field E, this is created by a point charge at a distance r away from the charge, and that's given by this equation. E is equal to k Q divided by R squared. E is the electric field, K is Coulomb's constant, Q is the charge creating the electric field, and R is the distance from the charge. Now looking at this expression, you notice that the electric field is inversely proportional to the square of the distance from the charge. This means that as the distance from the charge increases, the electric field decreases, specifically following a relationship where the field changes with the square of the distance. Now, the electric field at distance r, let's worry about that first. The problem gives us the electric field at distance r from the charge. It tells us that it is equal to 36 newtons per coulomb. So, we're going to use this as our reference point. At r distance, the electric field is 36 newtons per coulomb. Okay, keeping that as our reference point, let's work on determining the electric field at a distance 2r. At a distance 2r, we can go ahead and write our electric field expression. The electric field will decrease because the distance is now greater. So we can write that the electric field at 2r is equal to K multiplied by Q divided by 2r, and that's squared. So if we go ahead and expand that, that's KQ divided by 4r squared. Now what we notice here is this KQR squared. This is just our definition of our electric field at distance r. So our electric field at distance 2r is just 1 over 4 multiplied by the electric field at distance r. So this is 1/4 divided by multiplied by 36, and that gives us 9 newtons per coulomb. Now this makes sense because we said the distance increases, so our electric field will decrease. And that makes sense. At 2r, our electric field is smaller than it was at just distance r. So at r, it was 36 newtons per coulomb. At 2r, it's 9 newtons per coulomb. Let's figure out what this looks like for a distance of 3r. So we are also going to see something similar here. At a distance of 3r, the electric field will follow the same inverse square relationship. So the electric field will be even smaller. It will decrease even more because the distance is now greater. So we're going to write our electric field at a distance of 3r is going to be equal to kq divided by 3r squared. This looks like kq divided by 9r squared. Now this part of the equation looks like our expression for the electric field at distance r. And then what's left is 1 over 9. So this is 1 over 9 multiplied by the electric field at distance r. This is 1 over 9 multiplied by 36. This gives us 4 newtons per coulomb. So now we've figured out the electric field at a distance r, 2r, and 3r. It's 36, 9, and 4, which means the correct answer for problem 4 is going to be B. Let's tackle problem 5 next. This problem says a positive charge of plus Q is fixed at point R, a distance d away from another positive charge of plus 2Q fixed at point S. Point A is located midway between the charges, and point B is a distance d divided by 2 from plus 2Q as shown below. In which direction will a positive charge move if placed at point A and point B respectively? Let's start with placing a positive charge at point A. Now, this charge is going to experience a force due to the plus Q and due to the plus 2Q. Now, what we have here is a positive charge placed at point A, and it's surrounded on the left and on the right with positive charges as well. So it's going to experience repulsion forces from those two charges. Now, at point A, this positive charge is going to experience a force due to plus 2Q. Since it's repelling, it's going to be a force to the left away from plus 2Q. So the positive charge will experience a force to the left due to the plus 2Q. So we're going to note that. Now, it will also experience a force from this plus Q charge. That force will be due to the right, away from that plus Q charge. Now, point A, we said, is midway between plus Q and plus 2Q. So because point A is the same distance from plus Q and from plus 2Q, the force due to plus 2Q, it's going to be larger than that due to plus Q. And so there's going to be a net force to the left towards plus Q. Okay, so for positive charge placed at point A, all right, that positive charge is going to have a net force towards the positive Q charge at point R. Okay, so it's going to be a net force towards the plus Q charge, a net force towards point R. Okay, what about if we place a positive charge at point B? It's going to experience a repulsion force from both the plus 2Q and the plus Q. And they're both going to act on this positive charge, pushing it away from them to the right. So a positive charge placed at point B, all right, it's going to experience forces from both plus Q and plus 2Q that will point to the right. So there's going to be a net force to the right. Keeping that in mind, the correct answer for 5 is going to be C. In which direction will a positive charge move if placed at point A and point B respectively? It will move towards the plus Q charge at point A and towards the right at point B. So 5 is C. Let's do problem 6. Problem 6 says 2 parallel conducting plates are separated by a distance d. One plate carries a positive Q charge and the other carries a negative Q charge. The voltage between the plates is equal to 12 volts. If a plus 2 microcoulomb charge is released from rest at the positive plate, how much kinetic energy does it have when it reaches the negative plate? Okay, this is a great question. When a charge moves between 2 points with different electric potentials, its electric potential energy changes. For a charge Q moving across a potential difference V, the change in electric potential energy is given by this formula. Delta U is equal to Q times V. Delta U is the change in electric potential energy. Q is the charge, which in our case is plus 2 microcoulombs, which is equal to 2 times 10 to the minus 6 coulomb, multiplied by V, which is the potential difference, which is equal to 12 volts in our case. Now, as the charge is released from rest, all of that initial potential energy is converted into kinetic energy by the time it reaches the negatively charged plate. This is because the charge is attracted to that negatively charged plate, and it accelerates as it moves across the electric field. Therefore, the kinetic energy of the charge when it reaches the negative plate, that's going to be equal to the change in electric potential energy. Now, keeping that in mind, we can go ahead and start to calculate the kinetic energy using this expression. So K is equal to delta U, which is equal to Q times V. Q is equal to 2 times 10 to the minus 6 coulomb, and that's going to be multiplied by 12 volts. This is a really easy calculation. 2 times 12 is 24. And then we have here our times 10 to the negative 6. And our unit here is going to be joules. We can rewrite this to be 2.4 times 10 to the negative 5 joules. And this better matches up with our answer choices that were given. The correct answer for problem 6 is going to be answer choice C. Beautiful. Moving on to problem 7. Problem 7 says the negative charge in the figure below, minus 1 microcoulomb, moves from y equals negative 5 to y equals positive 5, and it's made to follow the dashed line. What is the work required to move the negative charge along the dashed line? Now, work is done on a charge when it moves in an electric field. The work done in moving a charge Q through a potential difference is given by this equation. Work is equal to Q multiplied by delta V. Now, in this case, we need to evaluate whether there is any change in electric potential as the charge moves along the dashed line. Notice that there are 2 positive 5 coulomb charges positioned symmetrically to the left and right of the path. Because of this symmetry, the electric potential due to the positive charges will be the same at every point along the y-axis. This is the dashed line along which the negative charge is moving. This means that as this charge, negative 1 microcoulomb charge, moves from y equals negative 5 to y equals positive 5, the electric potential at its location remains constant because it's equidistant from both positive charges the entire time. Since the electric potential does not change along the path, there's no potential difference, and this implies that the change in potential energy of the charge is 0. Without any change in potential energy, the work done to move the charge along this path is also 0. So the work required to move the charge along the dashed line is 0 joules, and the correct answer for problem 7 is C. Now let's do problem 8. Problem 8 says, if the magnetic field a distance r away from a current carrying wire is 10 Tesla, what will be the net magnetic field at that point at R if another wire is placed to R from the original wire and has a current twice as strong flowing in the opposite direction? Now, the first thing we want to do is take a look at our sketch. So here's this point that we're interested in calculating the net magnetic field at. We know that the effect of this wire, this first wire, is a magnetic field that's equal to 10 Tesla. When we introduce a second current carrying wire, that's a distance 2r from our original wire, what is that net magnetic field now at this point if this wire has a current twice as strong flowing in the opposite direction? The first thing we want to figure out is the magnetic field around each of these wires. And to do this, we need to use our right-hand rule. So looking at our first wire here, we want to take our right hand. We want to make sure our thumb is in the direction of current flow. And then we want to take the rest of our fingers and curl them in the direction of the wire. So if our thumb is pointing up and we curl our fingers, we see that the magnetic field on this side of the wire is going into the page. And on this side of the wire, it's going out of the page. Now we want to do the same for this second wire. Our thumb is going to point in the direction of current flow, which should be downward. And then we curl our fingers around the wire. We notice that at this side of the wire, the magnetic field is going into the page, and here out of the page. So this is good because right away we notice that between the two wires, the direction of the magnetic field is the same. It's into the page. Therefore, because the vector direction is the same, we can really just focus on the magnitudes of the two magnetic fields. We already know that the magnetic field due to the first wire is equal to 10 Tesla. What about the magnetic field due to the second wire? Let's go ahead and figure this out by first writing our equation for the magnetic field around a long straight wire. This is equal to mu naught, which is the permeability of free space, multiplied by the current, divided by 2 pi r. Now, for this second wire, how are we going to figure this out? Keep in mind, based off of this equation, magnetic field and current are directly proportional, while magnetic field and distance are inversely proportional. Therefore, doubling the current, this is going to result in double the magnetic field of the first wire. So here, since the only thing that's changing between wire 1 and wire 2 is the direction, which we already accounted for by figuring out the direction of the magnetic field in between the wires, and the second distance is the strength of the current, we can easily determine the magnetic field due to the second wire. It's twice the current, which means it's twice the magnetic field. And so the magnetic field due to wire 2 at this point is going to be 20 Tesla. And the total magnetic field is going to be B1 plus B2, 10 plus 20, and that's equal to 30 Tesla, specifically 30 Tesla into the page. And so the correct answer for problem 8 is going to be answer choice D. Let's move on to problem 9. Problem 9 says, given an electric dipole, the electric potential is 0 blank. Now we're going to work through each of the answer choices and talk about them, but first I want to quickly remind you about the electric potential of a dipole. An electric dipole consists of two equal but opposite charges separated by some distance. The potential at a point in space due to a dipole is the sum of the potentials due to each charge. The electric potential V at a point, a distance r from the positive charge, and r2 from the negative charge of the dipole is given by this formula. V is equal to KQ divided by R1 minus KQ divided by R2. We saw this in lecture, and here Q is the magnitude of the charge, R1 and R2 are the distances from the positive and negative charges respectively, and K is Coulomb's constant. Keeping that in mind, let's work through each of our answer choices. A says only at the midpoint of the dipole axis. Now, the midpoint of the dipole axis is exactly halfway between the two charges. While it might seem that the potential could be zero here due to symmetry, that is not correct. At this point, the potential due to both charges has the same magnitude but opposite sign, and the net potential is not zero because it's closer to the negative charge, making it negative overall. So here, answer choice A is not correct. B says anywhere on the perpendicular bisector of the dipole axis and at infinity. Now, on the perpendicular bisector of the dipole, the distances from the point to both charges are equal. Therefore, the contributions to the potential from both charges will cancel each other out, so mathematically this is going to be equal to zero. This means that anywhere on the perpendicular bisector of the dipole, the electric potential will be zero. Additionally, at infinity, the electric potential due to a dipole also approaches zero because both charges are infinitely far away. So answer choice B is correct. It's actually the correct answer for problem 9, but we're going to work through C and D as well. C says anywhere on the dipole axis. So along the dipole axis, the line connecting the two charges, the distance from a point to the positive and negative charges are not equal except at infinity. So as a result, the potential is not zero except at very far distances. So answer choice C is incorrect. And then answer choice D says only for points at infinity. While the potential at infinity is indeed zero, this is not the only location where the potential is zero. We've already established the potential is also zero along the perpendicular bisector of the dipole. So answer choice D is also incorrect, and that makes the correct answer for problem 9, answer choice B. Beautiful. Problem 10 is next. Problem 10 says an electron is accelerated over a distance d by an electric potential V. The electric potential applied to this electron is then increased by a factor of 4, and the electron is accelerated over the same distance d. The speed of the electron at the end of the second trial will be larger than at the end of the first trial by a factor of blank. Now, when a charged particle, like an electron, is accelerated by an electric potential, it gains kinetic energy. And the kinetic energy gained by the electron is related to the electric potential V as it travels through it. We've seen this formula before, QV for kinetic energy, but here we're dealing with an electron, so we can actually just write EV. So this is the charge of the electron multiplied by the electric potential. We also know that kinetic energy is also related to the speed of the electron by the equation that kinetic energy is equal to 1/2 mv squared. M is the mass of the electron, v is the speed of the electron. Okay, so now let's try to answer this problem. The work done by the electric field gives the electron kinetic energy. So we're going to go ahead and set these two equations equal to each other. EV is equal to 1/2 mv, and this is lowercase v squared. Don't confuse the two v's. This v is electric potential, and this v is the speed of the electron. Now that we have these equal to each other, we want to solve for the speed. So we want to solve for this little guy right here. So we want to isolate this variable. What we can do is we can multiply both sides by 2 and divide both sides by m. So that way we have v squared is equal to 2ev divided by m. We want to get rid of that square, so we can do the square root on both sides. And that gives us that v is equal to the square root of 2ev divided by m. Okay, now in the first trial, the electric potential is v. So the speed of the electron in the first trial is just v1 is equal to the square root of 2ev divided by m. In the second trial, though, the electric potential is increased by a factor of 4. So the speed of the electron is equal to the square root of 2e 4v, since we've increased it by a factor of 4, divided by m. This is, in other words, equal to the square root of v. We can just isolate that by itself, multiplied by the square root of 2ev divided by m. So essentially, the speed of the second trial, that's just equal to the square root of 4, which is 2, multiplied by v1. This is exactly the same formula as v1. So what we notice is that the speed of the electron in the second trial is twice the speed in the first trial. So the speed at the end of the second trial is twice the speed at the end of the first trial, meaning the speed increases by a factor of 2, making the correct answer for problem 10, answer choice D. Wonderful. Let's do problem 11 next. Problem 11 says which of the following accurately depicts the field lines created by a proton that is moving towards the right of this page. Okay, so what we're dealing with is a proton that's a positively charged particle. We should know that the field lines for a positively charged particle will always point away from the particle in a radial pattern, regardless of the direction in which the particle is moving. And this is because field lines point in the direction a positive charge would move in that field. That is, the direction that a force would be exerted on a positive test charge in that field. Nevertheless, the main point here is that the field lines for a positively charged particle will always point away from the particle in a radial pattern, and that is demonstrated in answer choice D. So 11 is D. What's demonstrated in answer choice A, just fun fact, would be the field lines for actually a negatively charged particle. Nevertheless, 11 is D. Let's move on to problem 12. Problem 12 says a certain 9-volt battery is used as a power source to move a 2 coulomb charge. How much work is done by the battery? The work done by an electric field or a battery in moving a charge is related to the electric potential difference, the voltage, and the amount of charge moved. The formula to calculate the work done in moving a charge Q across a potential difference is equal to Q times V. Again, Q is the charge, V is the potential difference in volts. Now, what we're given here is the voltage of the battery. It's equal to 9 volts, and we're given the charge moved by the battery. It has 2 coulombs of charge. So then the work done by the battery is calculated by multiplying the charge by the voltage. So 2 coulombs multiplied by 9 volts, and this gives us 18 joules. So the work done by the battery is 18 joules, and the correct answer for problem 12 is C. Now we can do problem 13. Problem 13 says, to increase the capacitance of a given capacitor, a dielectric is inserted between the 2 plates. Dielectrics are materials that block the flow of charge. Which of the following materials would be the best dielectric? Salt water, steel, glass, or copper? So the dielectric should be 1, a non-conductor, as conductors would allow current to flow and defeat the purpose of storing energy in the electric field. And second, have a high dielectric constant to maximize the capacitance. Let's work through the answer choices, starting with A, salt water. Salt water contains ions, which are free to move and conduct electricity. This makes it a conductor rather than an insulator, so it cannot serve as a dielectric. Salt water would allow current to flow between the plates, effectively short-circuiting the capacitor. So salt water is not a good dielectric, and this is not the correct answer. B says steel. Steel is a metal, and metals are conductors. Since conductors allow charge to move freely, steel would allow the flow of current between the plates and cannot be used as a dielectric. So B is also not the correct answer. C says glass. Glass is a non-conducting material. It's an insulator. It does not allow charges to flow through it, which makes it a really good candidate for a dielectric. Additionally, glass has a relatively high dielectric constant, making it very effective at increasing capacitance. And actually, the correct answer for 13 is indeed C. But we're going to go over answer choice D as well. D says copper. Copper is a metal, and like steel, it's a conductor. Conductors allow current to flow, and therefore, copper would not block the flow of charge between the plates, and it is not a good dielectric, so D is not the correct answer. Again, for problem 13, the correct answer is C. Moving on to problem 14. Problem 14 says a moving negative charge placed in an external magnetic field circulates counterclockwise in the plane of the paper. In which direction is the magnetic field pointing? To answer this question, we need to use the right-hand rule. Now, the velocity vector v, it's always tangent to the circle, and the magnetic force must always point towards the center of the circle. So consider when the negative charge is at the 12 o'clock position in this counterclockwise circle, and here we want to apply the right-hand rule. Your thumb should point to the left, tangent to the circle at that point, and then the back of your hand, which represents the force on the negative charge, it points down the paper towards the center of the circle. So in that case, your fingers must point out of the page to get your hand into that position. Therefore, the direction of the magnetic force must be out of the page. And the correct answer for problem 14 is B. Now on to our last and final problem for this set. Let's go ahead and tackle it together. Problem 15 says, many kinases have divalent cation cofactors to stabilize their interaction with ATP. If the electric potential energy of the cation and ATP is negative 3.3 times 10 to the negative 19 joules, how would the electric potential energy change if the distance between the cation and ATP were doubled? Now, the electric potential energy between two charged particles is given by this formula, K, Q1, Q2 divided by R. So here, Q1 and Q2 are the charges of the two particles, R is the distance between them, and K is Coulomb's constant. Now, just looking at this equation, when the distance R between the charges is doubled, the potential energy changes because it's inversely proportional to R. Specifically, if R is doubled, the new potential energy decreases by a factor of 2. However, in our case, because the two charges are oppositely charged, ATP negative, divalent cation positive, the initial potential energy is already negative. And when the distance is doubled, the magnitude of the potential energy decreases, but it remains negative. A smaller negative value still means an increase in the energy in terms of its absolute value, as moving farther apart makes the interaction weaker. So here, these are oppositely charged entities. So when oppositely charged species like ATP and a cation are moved apart, their potential energy will increase, reflecting the fact that these oppositely charged species would like to move back to a closer distance. So here, if the distance is changed by a factor of 2, then the potential energy will also change by a factor of 2, and it's specifically going to increase. So the correct answer for problem 15 is going to be A. And with that, we've completed our practice problem set. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.